Hi everyone. We just finished a lecture on energy and different types of chemical reactions. And so in this lecture, we're going to be talking about something called enzymes, which are molecules that help speed up reactions inside of your body. Okay, so in a lot of the molecules in the world, and for example like wood, there's a lot of potential energy stored in those bonds. And so the question is, why can't we just why don't they spontaneously combust and we can just get a bunch of energy from it? Well, the problem is there's needs to be some initial energy that you put in to that molecule in order to break those bonds and then release all of that energy. So even though molecules start with a lot of high potential energy, you need to put in a little bit amount of energy for it to break first, and then you release the energy inside of it. This amount of energy that you have to put in initially in order to break those bonds is called the energy of activation. This right here is a picture of an exergonic reaction, and you can see this part right here is the amount of initial energy you need to put into the system. And then once you put in this initial amount of energy, which is the energy of activation, then you release all of this extra energy. And so the net amount of energy that you actually release from the total reaction is just this amount right here, the difference between the potential energy of the reactants and the potential energy of the products. This right here is just the energy you have to initially put in order for the reaction to even start. So what are enzymes? How do they really work? Enzymes are biological catalysts that speed up the rates of chemical reactions. Most of the times, enzymes will be proteins or polypeptides, amino acids, made of amino acids. In terms of the structure of a protein enzyme, it looks like this, and there's usually something called the active site that the substrate fits into. And once that substrate, which is the molecule that the enzyme works on, once that substrate fits into its active site, the enzyme can actually break those two things apart. In some cases, actually puts things together, but this is an example of breaking things apart. So the enzymes work by lowering the energy of activation, so requiring less energy that you initially have to put in order for the reaction to start. Important to note, enzymes are not used up in the actual reaction itself. So they can help a reaction happen, and then they can just go back and help other reactions happen. They can be reused or recycled. As we mentioned before, that the word substrate is very important. Substrate is a name for the molecule that the enzyme is working on. And usually enzymes are very specific to only one type of substrate, maybe one or two. So that protein, that enzyme protein, is specially designed to work on only a very specific kind of molecule called the substrate. Just in terms of background information, the way you can tell that something is an enzyme is usually whatever name it is, it ends with this suffix ase, ace. It's like protease, I don't know, lactase. A lot of these things that ends with ase, that means that it's probably an enzyme. This right here is a picture of what the enzyme does to the energy of activation. So the black right here, this black line, is what the reaction normally would be. And so you can see that there's initially a lot of energy you have to put in order for the reaction to happen. But this red is what happens when you put in an enzyme. And you can see that it drastically lowers the amount of initial energy you have to put into the system for the reaction to occur. But notice that the net amount of energy that you actually gain from the system is the same regardless of if you have an enzyme or not. All the enzyme does is affects the amount of energy you initially have to put in, but the amount of energy you actually gain from the reaction is the same. So the question is, how do enzymes actually lower the activation energy? Before we talk about that, there are two questions we need to answer. One, what is the enzyme structure? And then two, how does the enzyme actually work? So we discussed a little bit about the enzyme structure, but just to reiterate, this right here, there's a specific active site, and the active site is where that substrate of the enzyme binds, and that's the specific place where there's a reaction that occurs. So this is the process of how an enzyme works. You have the enzyme with the active site, and then it binds right here to the substrate, and then it does something called induced fit. This is a really important term that I would write down in your notes. Induced fit is when the active site, as soon as it kind of binds with the substrate, they kind of change shape a little bit, both the enzyme and the substrate, to make the fit even better. And that change of shape is called induced fit. And this right here is the definition. And so that induced fit makes it even better for the enzyme to help break down that substrate or reform a substrate. And then water will come in a process, remember, called hydrolysis, and then it will convert that substrate down into its products. And here the products are released. Now it's just important to remember that this example that I just shared was a hydrolysis reaction. There are cases in which enzymes will help put two different molecules together in a dehydration reaction, which would be the opposite process. So enzymes can do both kinds of reactions. This is a really important slide that I would star in your notes, and this is information that is not inside your textbook, but I do want you to know it. There are three different ways that the enzymes can kind of make make reactions happen faster. In one case, an enzyme can actually bring two substrates closer together in space. And then this is really important for kind of dehydration reactions where you need to have two molecules that come together to form a new molecule. And so the enzyme, it helps bring them closer together so the reaction happens faster. In this case right here, when the substrate binds into the enzyme, it kind of just, it helps like the charges align so that the reaction just happens more favorably. So this right here is about kind of aligning the electronegativity or the different charges of the actual substrate. And then this case, this is probably the one I think your textbook talks about, but the enzyme can actually strain the substrate, so kind of squeeze it or bend it so that it's easier for it to break. So this one right here is most relevant for hydrolysis reactions when you're trying to break down a substrate. So this is dehydration. This is just in general for any types of reactions. And then this one right here is for hydrolysis reactions. Okay, this is important. This shows what happens to an enzyme when you add a lot of substrate over time. And so initially, the more substrate you add, the faster the reaction will be. But you hit a certain point where it starts to plateau off over here. And the reason why that is because eventually at some point the enzyme gets saturated with a lot of substrate so that it can't make the reaction faster because it's working at its maximum capacity and there's so many extra substrates that as soon as it finishes breaking down one, there's an extra substrate it needs to break down. And so here is when this is kind of the maximum capacity of the enzyme to work. This is the maximum rate that the enzyme can work. There are a couple things that affect enzyme activity. One of them is temperature, and this shouldn't be a surprise to you because we know enzymes are proteins, and so because enzymes are proteins, they're susceptible to being denatured. So there's a very specific temperature that enzymes like to work at. For your enzymes inside your body, they tend to be optimal at like your normal body temperature. The other thing that affects enzymes is pH. So the acidity or basicity of the solution will also affect the enzyme. This right here is just a picture of how pH affects the enzyme. This right here is an enzyme that would work at acidic conditions, and this right here is just a representation of an enzyme that works at basic conditions. There are a couple things that can help your enzymes. One of them is cofactors, and so those are things that are inorganic, which means they're just usually metals like zinc or iron or copper. They're not really like actually molecules, they're more like metals, and they just help your enzymes work. And the other thing is called coenzymes, and coenzymes are usually organic molecules, and they can be things like vitamins that they help your enzyme function better. On the opposite end of the spectrum, there are something called inhibitors, and inhibitors prevent the enzyme from working. And so there's different types of inhibitors for your body. One of them is called competitive inhibitors, and what they do is they're kind of almost very similarly shaped to the substrate, and they can bind at the active site. And so when the inhibitor that's competitive, when it binds to the active site, it blocks off the actual substrate from fitting in, and so the enzyme can't really do its job. This right here is a picture. This blue is the competitive inhibitor, and so you see that it prevents the substrate from binding to the active site. The other type, something really important about this is that competitive inhibition can be overcome by increasing the amount of substrate. And so what I mean is, this right here is blocking the enzyme, right, the inhibitor. But if you just increase the amount of substrate, if there's just so many substrates that are around the enzyme, it kind of knock off that inhibitor and just allow the enzyme to do its work. So competitive inhibition can be prevented by increasing the amount of substrate. The other kind of inhibitor is non-competitive, and it doesn't bind to the active site. It actually binds to a different part of the enzyme, and when it binds to a different part of the enzyme, it changes the shape of the enzyme and thus changes the shape of the active site so that substrate can't really fit in very well anymore. And this kind of inhibitor it's irreversible, which means that you can't really change its effect by increasing the amount of substrate. This right here is an example of non-competitive inhibition, and you can see this is the non-competitive inhibitor where it binds somewhere else, not the active site. And because it binds here, it changes the shape over here of the active site, so the substrate can't really fit anymore. So enzyme inhibitors are important in regulating reactions. Just because they prevent an enzyme doesn't mean it's a bad thing. Sometimes that's exactly what your body wants to do. And so there's something called feedback inhibition, where your body is very clever and it doesn't want to overproduce a product. And so in order to prevent that from happening, it will allow its product to inhibit the reaction, so that once it's clear that a lot of products are being made and that reaction is going well, those products will actually start to prevent that reaction from happening, and it kind of keeps things in balance. And this is an example of negative feedback where these enzymes are helping this reaction eventually form D. But once you have a lot of Ds formed, these Ds actually kind of inhibit enzyme 1 from working. So that means that when you have too much D, it'll actually stop the reaction from occurring so that it'll lower the amount, it'll kind of keep it in balance. And then when you have too little D, then there's not that many inhibitors for enzyme 1, so the reaction will continue to occur. And that is it. Thank you so much for watching.